progress and you reach there. That's for a well-conditioned problem. In an ill-conditioned problem, it takes you even larger. In a neural network type problem, which is non-convex, you have to typically work with smaller step sizes, and if you take bigger ones, you can get crazy oscillations, but that's gradient descent. In comparison, let's hope that this loads correctly. Oh, there's even a picture of Robbins, who was the co-discoverer of the stochastic gradient method. There's a nice simulation that instead of making that kind of deterministic descent, after all, gradient descent is called gradient descent. At every step, it descends, it decreases the cost function. Stochastic gradient descent is actually a misnomer. At every step, it doesn't do any descent. It does not decrease the cost function. So you can see at every step, those are the contours of the cost function. Sometimes it goes up, sometimes it goes down. It fluctuates around, but it kind of stochastically still seems to be making progress towards the optimum. And stochastic gradient descent, because it's not using exact gradients, just working with these random examples, it actually is much more sensitive to step sizes. And you can see as I increase the step size, its behavior. This is like actually full simulation for a toy problem. So initially, what I want you to notice is, let me go through this a few times. Keep looking at what patterns you may notice in how that line is fluctuating. Hopefully this is big enough for everybody to see. Okay. So this slider that I'm shifting is just the step size. So let me just remind you in case you forgot the iteration. We are running xk plus